Firstly, let me thank the organizers, Garrett, and of course, Jairo, for supporting this workshop, because it's a very exciting workshop where I learned a lot. There are a lot of exciting talks that I didn't know about. So at least for me, there was a very steep learning curve. And so I'll try and to keep you entertained for the last talk of today. I know I'm the last thing between you and dinner. So I will particularly talk about two topics. And I've put the names because some of the people that are involved are also here. So the first part of the talk will be on magnetic properties of magnetic insulators probed by spin Cavitronics. So that actually is really part of the title of this workshop. And the work was all done by Isabel Boventa together with Martin Weides, who you heard earlier this morning. So this will be an extension or some part of the work that we did together. And then the second part is lateral spin transport in anti-ferromagnetic insulators. So this is more related to the talk that you've seen from Sebastian Gönnenwein. And in particular, I'll look at the superfluid regime and the diffusive regime. And this work was done primarily by Robin Lebrun, Andrew Ross, and Scott Bender. Scott Bender, theory in the group of Rambert Deune, experiments in my group together with Arne Bratas, and some of the work also with my chairman, and supported by NTNU. So let's start with the part on the spin Cavitronics. So I'm not a fundamental quantum person, so my interest in this field was to actually characterize some of the magnetic properties of the materials using spin Cavitronics. So firstly, okay, the beast, you've all seen it. No need to go into details again. But I wanted to, in addition to showing you the theoretician's picture of YIG, so this is courtesy of Joe Barker, I also actually want to show you a real image. What does YIG look like? And particularly in this case, gadolinium iron garnet. So this is what it really looks like. So this is now gadolinium iron garnet on gadolinium gallium garnet. And what you see is that there's an extremely abrupt interface where you have the gadolinium and the iron and the gallium and the iron, the gadolinium and the gallium versus the gadolinium and the iron, and it's extremely well ordered. So if you look at where the different atoms are expected to be, it fits really well. So I was very impressed because it's a large unit cell. So sometimes you really wonder how nature allows you to make such a perfect crystal at the interface. And that is, I think, at least to me, still one of the biggest miracles, that such a complex material is liked by nature. And it has good properties as well. OK, so this is the material. So we've been looking at YIG as well as other garnets. And the first thing we did is, like everyone else, we put a YIG sphere into a microwave cavity to combine the magnon and the photons. And this forms the polariton quasi-particle. Again, nothing new. The reason that we looked at that in a bit more detail is that there were, when we started off this work, there were some reports about the spectroscopy at room temperature and 20 millikelvin. And we wanted to look at the full temperature range to learn a little bit about the temperature evolution, which turned out to be more complex than we originally thought. So together with Martin Weides, we could go down to 30 millikelvin and then go up to room temperature and look at the properties that govern this polariton formation as a function of temperature. So this is our setup. So we use this reentrant cavity. This was done by Isabel together with the people in Karlsruhe. And then we place the YIG in one of the antinodes. And we have the feed line to connect to the microwave source of our vector network analyzer. And we can either measure in reflection or transmission. And it turns out both give consistent results for us. So here's a typical image. You've seen already 24 of those in the last couple of days. You have the photon mode, the cavity mode, which is field independent, and you have the YIG, the magnon mode, which is field dependent. So at resonance, then, you have this avoided level crossing. And now we want to look at the parameters that govern this polariton formation, which is the coupling constant, which you see here. So this spacing here is just 2 times G effective. So to analyze the data, we model this using this input-output theory. This S11 is the reflection parameter, and it's essentially governed by the kappas. Kappas are all the losses. So in this case, it's external coupling losses, and this is the losses due to the cavity as well as the transmission line. And then in particular, we are interested in the losses due to the magnons. And then, of course, in addition, you have the coupling constant, which is the first approximation proportional to square root of the number of spins times the spin, so the total magnetic moment, the square root of the total magnetic moment. So that was the aim, to understand how these two depend on temperature and learn what governs them. So then we measured, so the first thing we measured is this effective coupling constant as a function of temperature. And so we see here we went in one of the cryosystems down to 4 Kelvin, and then in the other cryosystem we went into the millikelvin regime. So I didn't put more data points here because this was shown by Martin Weides already earlier today. And what you see is that, okay, you decrease the temperature, the coupling constant goes up, but then somehow it levels off. And if you remember that the coupling constant should be proportional to the square root of the number of spins, and the saturation magnetization is just proportional to this number, then you can plot both the saturation magnetization and the effective coupling constant, and you see that for large temperatures, this fits. But at higher temperatures, at lower temperatures, you actually get a saturation here which does not fit the simple MS. So the scaling that the effective coupling just scales with the square root of the number of spins doesn't work if you compare these two curves. So the question was, okay, where does that come from? And so we had to look a little more in detail. So yeah, we just modeled this with Loch's T3/2 law. And what we found is that if you look very closely, there's not just one mode, but there are other modes as well. And in particular, so this was all done for the same sphere, we see that these modes, as you reduce the temperature, they can become degenerate to this normal, say, majority Kittel mode. And then this means that you have a coupling not only to this Kittel mode, but also to these other modes. And this is one way to interpret that this change at low temperature, where you have this degeneracy as these two modes move towards this mode here, and this can explain the reduction in the coupling to the Kittel mode, which we in the end measure. We don't measure the coupling to this, these extra modes here. So above 100 Kelvin, it fits well, where these modes are far away from the Kittel mode. Below 100 Kelvin, we find that as these modes move towards the Kittel mode, you get a change due to this additional coupling to the higher order magnetostatic modes. So the second thing is we wanted to look at the losses. And so if you now look at the magnonic losses as a function of temperature, you see it looks rather complex. So it's strongly non-monotonous. So you see as you reduce the temperature from room temperature, the losses go up. They peak here at something like 50 Kelvin, or a little lower than 50 Kelvin, and then they go down to the millikelvin regime. And then you could see, and this was also already shown in 2013 by the Tokyo group, that then it levels off at very low temperatures in the tens of millikelvin regime. And we get a minimum at a few hundred millikelvin. So the question is a little bit, where does that come from? You see also, well, the blue and the red data is transmission and reflection, and within the error bars, this is the same data. So there were different interpretations. So Martin already discussed with you that at very low temperature, you have these two-level system fluctuations which govern the losses. And then as you increase the temperature, this increase here is interpreted as to result from impurities, in particular other rare earth atom impurities, which then lead to stronger scattering. And theoretically, this peak here, and it looks a little bit like a shoulder here, they could tell you something about what type of rare earth impurity it is. But at the moment, we don't know. So this is, at the moment, we don't know if there's one or two types. And we don't know which type of impurity it is. But this is the model as put forward, and our results are consistent with that. If you look at the cavity dissipation, we see that's rather flat. Well, we don't have a superconducting cavity, so not much happens in the temperature regime that we look at. But what is most important, if you want to use this for coherent information exchange between the magnon and the photon system, you need to look at the corporativity. So this corporativity here essentially is a measure whether you're in the strong coupling regime or not. So if it's larger than 1, you're in the strong coupling regime. If you're lower than 1, you're not. And what you see is that if you start at the lowest temperature, you have something of 100 or 120. And even at the minimum, you get something like 20 for the corporativity, which then goes back up to 300. So you're always in this a strong coupling regime, which means that over the whole temperature range, you can coherently transfer information between the phonon and the magnon regime, which is quite interesting because this is for many systems not the case, that at high temperature you go into the low coupling regime. All right, so this is all that I wanted to show you. The paper is here. You can read up the details. But yeah, the paper came out just in time yesterday, so thanks to PRB for that. Well, we did nothing, no intervention from our side. So essentially this method, which I think it's interesting because it allows you to learn something about the system and about the materials that we look at. In this case, it was a simple YIG sphere. You can do the same analysis, which is laid out here in this paper, also for other systems, and learn something about the temperature dependence of the different properties. So let me then now switch to actually using these materials, using these insulators for lateral spin transport. So spin transport, we've already learned in these insulators, is extremely exciting because you have no moving charges, so there are no ohmic losses, and also because these insulators have low damping, because there are no electrical degrees of freedom. This allows you then to transport spin information, theoretically at least, over large distances. So this is a very schematic way of sketching what we do. So we have our insulator here. We have two heavy metal bars, so usually this is platinum. We drive an electrical charge current through this bar. This then injects a spin current in our insulator, and then here the spin current moves back into the platinum and generates a voltage, which we then measure. So this was first pioneered by the group of Bart van Wees, and we did some work together with Sebastian's group on that for ferromagnets, so for YIG, and people have been trying to adapt this for antiferromagnets. So the way it works is that for those of you not coming from the community, the spin Hall effect just converts a longitudinal charge current into a vertical spin current by having, say, the spin right electron scattered to the, let me just show that again, spin right electron scattered to the top interface, spin left electrons to the bottom interface, and they then diffuse across the interface into a ferromagnet or antiferromagnet. They can manipulate the magnetization or can be transported. We just put this upside down, so in our case the heavy metal is on top and the material which transports the spin is at the bottom. Right. So now there was this prediction by Jaroslav, by people from Arne Brathaus' group, from Alan MacDonald, that you could have transport not only in this typical diffusive regime, which has been probed in YIG, but also in the superfluid regime, where you have this coherent rotation of the Néel vector, the order parameter, in an easy plane, and you can transport spin in a superfluid regime. And the signatures of this is that you have a threshold current density to overcome the anisotropy barrier and a linear or nonlinear spacing dependence to distinguish between this superfluidity, where you should have a linear spacing dependence, and if you have an exponential spacing dependence, it should be diffusive. So there's a first claim that this has been observed, but at least at the last Intermag conference, this was very critically reviewed because they only show second harmonic measurements based on the spin-Seeberg effect, nothing on the first harmonics. So I am not very convinced that this really spin superfluidity, but it has created a lot of interest, and so of course also from our side. So the first thing we did was actually our chairman and myself. We did some calculations on how to maximize this superfluid spin current. And it turns out that as you increase the charge current, you get a maximum of the spin current at some injection. And if you increase the charge current further, the Néel vector tilts, and then you actually decrease the spin current, so that actually there is a maximum of the spin current that you can generate at a finite value of the charge current. And another nice thing about the spin superfluidity is that you have this hydrodynamic equivalent, that if you have here an injection of a width W and you have a spin conduit which has a much smaller width small w, let's say if big W is 10 times small w, then you can generate a 10 times larger superfluid spin current in this spin conduit. So we looked at that, and the first material that we looked at is nickel oxide, because everyone said you should try nickel oxide, so we tried nickel oxide like everyone else. And I'll show you some results which have never been published and will never be published, because it turns out that nickel oxide is not as easy as you think. So the first thing is we measured a signal over 150 nanometer distance, which looked very nice. And you see that as you increase the field at roughly the spin flop field, you get an increase of the signal. However, it turns out if you touch the sample and squeeze it to change the domain structure, this behavior can change drastically. So if you measure 10 samples under 10 different conditions, 10 times under nominally the same condition, you get very different effects here. So we don't know what this is. Could be spin superfluidity. Turns out that nickel oxide is a very subtle material where you have to be very careful about the interpretation. So in general, I think antiferromagnets are much tougher than ferromagnets. So if you work on that, make sure it's robust. So this, we don't know what it is. We have spin transport in nickel oxide, but it is changing depending on the samples. And also, if we increase the spacing, we get a non-monotonous dependence of the signal amplitude on spacing. So sometimes more spacing makes higher amplitude. So we don't know. The nice thing about superfluid spin transport is that you can actually do also logic with it, because you have this coherence of this rotation of the near order parameter. So in these papers here, they suggested that you can use spin waves and the wave nature of the spin waves for logic by having, for instance, constructive or destructive interference of two magnons propagating in these two arms. However, they needed 18 gigahertz to excite these spin waves. Now, in case of a superfluid spin current, you can have a DC excitation here, which generates these two coherent spin flows, JS1 and JS2, which can then interfere here at the detector. And depending on if you have a gate voltage on or off that changes the magnetic properties below one of the arms, you can have also these effects, which then lead to a possibility to have a logic which is operated by DC, not by such AC excitations. So this you can read up. It's all theory in this paper here. And now we come to the things that actually work. And it turns out that if you look at how to transport spin and antiferromagnets in the diffusive regime, it's not so obvious. So you have firstly your Néel vector, which contains the two sublattices, red and blue. And if you then apply a field, you can cant the two sublattices and generate a small magnetic moment. So how can these two effects transport spin angular momentum? Now, the first one here, you have the magnon modes of the two sublattices, which generate an angular momentum because you have a small magnetic moment precessing like that in this direction, so along the Néel vector. So that's important. So the angular momentum is pointing along the Néel vector. Now, in case that you have the spin canting and the net ferromagnetic moment, the angular momentum is perpendicular to the Néel vector. So remember these two different types of spin angular momentum transport. Now, the problem is, of course, you have, for instance, for this mode here, you have two degenerate modes, which a priori are energetically degenerate, but carry opposite spin angular momentum, so they should simply cancel out. So the total transport of spin current is 0, even though you have each of these modes transporting spin. So how can you get over that problem? So what you can do is you can inject spins through this platinum wire and generating a spin bias at the interface, which then changes the population of these two modes. And if you have more magnons of this mode here than here, you can transport a net angular momentum. And so this is what we set out to do. And the first thing we wanted to know is, of course, in which direction does the Néel vector point. And to do that, we do a spin-Hall magnetoresistance just as a preliminary measurement. And we see that at 0 applied field in this material, which is alpha Fe2O3 hematite, which is an easy axis material, our Néel vector, which I denote here with this blue arrow, is just pointing along the easy axis. Now we apply a strong field, and then we will tilt by the spin flop this Néel vector in a direction which is perpendicular to the applied field, and we can detect this very nicely in the measured spin-Hall magnetoresistance. So this allows us, you can read up, this is the paper with Sebastian and Egi and some of our recent work, where you can simply see that you can detect the direction of the Néel vector by the spin-Hall magnetoresistance. Now the next step is to actually do lateral transport by putting a second ferromagnetic contact on here. And now let's again look at the signal that we measure here. Here's the injector, here's the detector as a function of applied field. And now we have to remember which directions do we have the platinum wires attached and which direction is the field. So fundamentally, there are 4 combinations. We have an easy axis this way. So we can have the platinum wires along the easy axis and the field parallel or perpendicular, or the platinum wires perpendicular to the easy axis, and again the field along and parallel and perpendicular. So let's see. Indeed, what we see is we see a very nice signal in this geometry, which starts to increase at the spin flop field. So at zero field, so here is the first harmonic signal, which is essentially the transport due to the Néel vector precessing. And this is the second harmonic signal, which is the spin-Seebeck signal, which is due to this canting and the generated ferromagnetic moment. And we see that for this geometry, we have an increase in the signal at the spin flop field. And then it goes down, but it doesn't go down back to zero, but stays finite. So how can we explain that? So let's start at zero field. We see here the Néel vector is parallel to the easy axis, but perpendicular to the injected spins from the platinum. So there should be no signal, because you see here the transported spin is parallel to the Néel vector, and here it's perpendicular, so there's no coupling from here to here. If we now apply a field, however, we rotate the Néel vector along the injected spins, and now it works. Now we can transport spin by this mode into the other platinum wire here. And this is exactly what we see. So at the spin flop, we get an increase. So just because of the geometry, the Néel vector is pointing in the right direction. We are now able to transport spins using this, what we call spin-bias spin transport. Now, the question is not only why is there an increase, but also then why does it decrease again and then flatten off? And the reason is that you have an increase here. It works from the geometry, but also you close the gap. And as you close the gap, you have more magnons that can transport the spin. But if you then increase the field further, you open the gap again. And therefore, the signal goes back down. And the group of Rembert-Deune and Arne Bratas, in particular Scott Bender, they calculated this for our geometry and found that it fits really well. So here at the spin flop, you get this peak, and then you get a reduction of the signal as you increase the field and reopen the gap.
What is the temperature?
200 Kelvin.
Such small changes in the field, would not change. So the gap changes on the scale.
That depends which magnons carry the spin current. I mean, in that sense, it's a question of which magnons do we freeze out the interesting magnons, and apparently we do.
It's just funny that the theory gives you also such a. So that, I mean, they must have done something a bit funny in the theory.
Have a look at the paper. I mean, I can explain to you the theory later. So what is yeah. But let's first go through the different geometries. Let's just check if qualitatively the geometries fit. Now what we look at is the second harmonic. So now we look at just the heating signal. Again, what we expect is that if we apply a field, we get a change of the spin Néel vector in the direction perpendicular to the field. So the canting leads to a net magnetic moment along the field. And this net magnetic moment can now not couple to the injected spins here. So you don't expect for this geometry that there is a sizable spin-Seebeck signal. And this is what we see here. It's roughly zero within our error bar. So this looks fine. Now we change the geometry. And now what we do is we apply the field not anymore along the easy axis, but along the hard axis. So let's see first for the spin-Seebeck signal. Now if we have zero field, of course there's no canting. So this means there is no net magnetic moment. So at zero it should be zero. And now as we apply the field, we see that we start to cant the Néel vectors, so the sublattices, and therefore a net magnetic moment starts to occur in the direction parallel to the injected spins. And so you expect that the more you tilt the sublattices, the larger the ferromagnetic moment and the larger the spin-Seebeck signal. And this is exactly what we see here. While for the first harmonic, so the spin bias, there should be no signal because, as we apply the field, the Néel vector will always stay in a direction which is perpendicular to the field along the easy axis and therefore perpendicular to the injected spins. So this means in this geometry, the spin bias is not possible, but spin-Seebeck transport is possible. The more canting you do, the more signal you get, which is consistent with our results. Now finally, we change the direction of the platinum bars. You see here the platinum bars are along the easy axis, and now we put the platinum bars perpendicular to the easy axis. And in this case now, the nice thing is that even at zero applied field, we already have the Néel vector along the easy axis in a direction where it can transport spin. And this is exactly what we see. We see that the signal at zero field is already large because the orientation of the Néel vector, which carries the spin angular momentum, is already in the right direction. So we can get long-distance spin transport even at zero field. And now if we apply a field, then the Néel vector will rotate in the direction which is now perpendicular to the injected spin. So at the spin flop, the signal should go down. And it does. You see at the spin flop, it goes back to zero. But then, of course, the spin-Seebeck signal goes up because now we have the canting, and the canting is in the right direction. It's parallel to the injected spins, and so you get this increase with increasing field. So to summarize that, so the spin-bias transport at zero field is possible for this geometry, and the spin-Seebeck transport is possible for high fields where you have done the spin flop. And this means that the spin-bias transport depends on n, so on the Néel vector, and the spin-Seebeck depends on the induced magnetic moment. It's also clear it has to, because spin-Seebeck, of course, doesn't break the symmetry otherwise. You need to break the symmetry somehow to transport net angular momentum. And the spin-Seebeck does it by using the net magnetic moment, and the spin-bias does it by biasing the two antiferromagnetic modes of the Néel vector. All right. So now let's look at the distance dependence, and then we were very positively surprised of this material after having gone through a lot of measurements with nickel oxide, where if you do at vertical transport, we get a spin diffusion length of 5 nanometers. Now here you see that we can get a signal at 40 micron distance. And initially the student who worked on that, which is Andrew Ross, his tentative title for his thesis was spin superfluidity. So we started to measure here and said, oh, it's fantastic. It's completely linear. So how about we call this spin superfluidity? And then I said, like after also talking to Bart, we should measure the full range. And you see that actually it's not true. We see that at large distances, there is a clear exponential decay, meaning that this is not spin superfluidity. But the nice thing is that even in this diffusive regime, the spin diffusion length is 9 microns. And also, it depends on the orientation. So that's also important. So the spin diffusion length depends on the direction in which you transport the spin. So to show why we think it's not spin superfluidity, but diffusive transport is, we don't have a threshold. It starts at 0 and goes simply linearly up with increasing current density. It's visible at high temperatures. This was measured at 200 Kelvin. It works also at other temperatures, but it's not like it only works at 4 Kelvin. And we see an exponential decay. So in this case, we believe that this is diffusive transport over tens of microns in this easy axis antiferromagnet, whereas previously, if you look at the papers also shown by YIG, in this vertical transport by using nickel oxide, cobalt oxide, many other oxides, the spin diffusion length found was only 2 nanometers, 5 nanometers. So this is 2 orders of magnitude more. All right, that's it. This is the most important slide. So the people that did all the work are here on this photo, and additionally, of course, Martin Weides. We have good collaboration with our colleagues at Tohoku University, with YIG's group and Garrett, with people in Mainz, with Sebastian and Rudi Großgrupp and Hans Hübel, with people at NTNU, Arne Bratasch, Scott Bender and Rambert Deune. They've been instrumental in the theory, and with Jaroslav on the spin superfluidity. Okay, nothing would work without the funding, in particular new EU project on anti-ferromagnetic spintronics. And so to sum it up, so we've used the temperature dependence of the spin Cavitronics measurements to determine the coupling strength and the dissipation. We have looked at superdiffusive transport in easy plane antiferromagnets. Theoretically, it works well, practically difficult. And we have looked at diffusive transport in easy axis antiferromagnets with low damping. And in particular, we've identified the need to probe length scales much larger than the spin diffusion length to separate between diffusive transport and superfluid transport. If you're interested, here are the papers. And with that, I thank you for your attention.